All right, we're picking up where we left off, going over the inverse trig functions. So we just learned about the inverse sine function. Now let's take a look at the inverse cosine function. So here's inverse cosine, cosine to the minus 1 of x, or y is equal to arc cosine of x. And what we're going to do is, in the same idea we did with sine, that they draw out cosine, and it's not a one-to-one function, so we want to apply a domain restriction to cosine, and we're just going to restrict the domain to where we have the full range of cosine going from -1 to 1 and no more than that, so that's going to be a half of a period. If we went a full period, we'd go over all of the y values twice, but that's a full period, because you go from 0 to -1 going down, then you go from 0 to 1 going up. As far as a period is concerned, that's two different regions. As far as restricting the domain to where it's a one-to-one function, we only want to go over map out the outputs of the cosine function one time. So we go from 1 to 0, and then from 0 to 1, and that's it. And we could technically choose any range of x values along the full domain, going from -infinity to infinity, as for the definition of the inverse function. But what they do is they choose the simplest. So for the sine, that was from -pi/2 to pi/2. Here, the simplest is from 0 to pi. So to get the inverse of cosine, we're gonna the inverse cosine function. There is no inverse function for just cosine of x. This is not a one-to-one function. This has no inverse function. However, if we say cosine of x strictly from 0 to pi, including the endpoints, this is now one-to-one. This we can get an inverse. And so the inverse is, just like we did with sine, I'm not going to do it again, but you take the inverse of both sides with the notation they get for inverse. And so the inverse of this is y is equal to cosine -1 of x, or that's this here. And we can look at the graph of that by flipping this about y is equal to x. So let me bring in a graph. Okay, so in the blue, that's cosine x with the restricted from 0 to pi. And then there's y is equal to x. And you see, you just flipped the blue curve about y is equal to x. And you get, there's inverse cosine. Okay, and the domain is going to, so we restricted the domain of this to be from 0 to pi, and the range we know is from -1 to 1. So now with inverse cosine, the domain is going to be from -1 to 1, and the range is going to be from 0 to pi, and that's what you see here. Domain from -1 to 1, and the range is from 0 to pi. With sine, the domain was the inverse sine domain was -1 to 1. The range was -pi/2 to pi/2, because that's how we know that's how inverses work. The domain and range flip. The graph flips about y is equal to x, and the domain and ranges flip. Okay, so there's the inverse cosine function. Y is equal to cosine -1 of x, or y is equal to arc cosine of x, means that x is equal to cosine y. It's saying that the output of arc cosine x is that it's an angle to where if you took the cosine of that angle, you would get what the argument that you put in to the inverse cosine function. All right, and it's only for the angles it's going to give you are strictly from 0 to pi, something from 0 to pi, and that's it. Okay. So, what would arc cosine of 1 be? Well, okay, we know that this is asking if we took a cosine of an angle and got 1. So what was that angle that we took? What was the angle? Well, based on the definition of inverse cosine, we're gonna get some angle between 0 and pi, because going from 0 to pi, all possible outputs of cosine are represented. So it's going to be an angle in that region. So what angle between 0 and pi, when you take the cosine of that angle, do you get 1? Well, we know that's when the x is equal to the radius, but the x is in the positive direction. So that's x is equal to the radius here when theta is equal to 0. So this is 0. And that's it. Now, technically, though, again, you want to think about, though, that, yes, the answer to the arc cosine of 1 is only 0. But as far as the general question you're asking, what angle, when you take the cosine of that angle, do you get the value of 1? The answer to that question in general is 0 degrees or any angle that's coterminal with 0 degrees. Okay. Now, what about inverse cosine of minus root 2 over 2? So here's the initial side, and okay, what angle, when you take the cosine of that angle, do you get minus root 2 over 2? And so it's going to be something between 0 and pi. We know cosine is positive in quadrant 1, negative in quadrant 2. So this is going to be something in quadrant 2. So let's go ahead and draw that. Something in quadrant 2. Okay, so now if we think about root 2 over 2, 1 over root 2 is equal to root 2 over 2. It's been rationalized. And so we know the 45, 90 triangle has sides. Okay, so that means that we know that the reference angle is going to be 45 degrees. So theta is going to be 135 degrees. Because in that case, we're going to have minus 1 root 2. The cosine of this reference angle is minus 1 over root 2. That's minus root 2 over 2. So this is going to be 135 degrees, or I guess they'd want it in radians. But you could degrees is you could do it at any angle you want. I'll put it in radians for now. So 3 pi over 4. That's 135 degrees in radians. Okay, so that is the only answer to this question, to the inverse cosine of minus root 2 over 2. However, it's going to be common practice to think about, you're going to look at your problem and think about, okay, but what in general, what angles answer the question here? That when you take the cosine of that angle, you get minus root 2 over 2. And, remember, you might be tempted to say, oh, well, it's just any angle that's coterminal with 135. That is true. However, when it comes to the non-quadrantal angles, it's actually a little bit more than that. So we know it's going to be any angle to where cosine is negative and also has a reference angle of 45. So cosine is negative in quadrants 2 and 3. So if you take the cosine of an angle in the third quadrant with reference angle 45, so that would be what? 180, that's 225. The cosine of 225 minus root 2 over 2 also evaluates to minus root 2 over 2. So any angle that 135 or any angle that's coterminal with 135 or 225 and any angle that's coterminal with 225 satisfies that question of when you take its trig function, when you take its cosine value, you get minus root 2 over 2. Okay. However, that does not mean that this has multiple answers to come out of this function. This has one and only one answer. 3 pi over 4 or 135. Okay. So now here's a summary of the inverse cosine, domain minus 1 to 1, range 0 to pi. Here's the graph. It's continuous. It's decreasing. Sine was always increasing. This is always decreasing. Inverse sine was always increasing. And it doesn't intercept the origin like inverse sine did. It has one y-intercept and one x-intercept. The y-intercept is at 0 pi over 2. The x-intercept is at 0, 1. And then what's interesting is that there's no symmetry here. It's not even or odd. Inverse sine was odd. Here, this has no function symmetry. It's not even or odd. Okay. Now, let's talk about inverse tangent. Okay, so it's same idea. We're going to need to, it's a periodic function, so we're going to need to restrict the domain to make it 1-to-1, and we're just going to pick the simplest, the simplest domain restriction. So we know that tangent is like the base period that we would sketch. We would go from minus pi over 2 to pi over 2, and it went something like this. Okay, and in order for roping off a domain restriction to make the function 1-to-1, we want to encompass the full range of the function. So with sine and cosine, that was minus 1-to-1, but we know with tangent, that's negative infinity to infinity. It's any number you can get out of tangent. So to encompass any number from negative infinity to infinity, we can just use this. We can say, okay, we want to find the inverse of y is equal to tangent x. This has no inverse function, but when we restrict the domain to minus pi over 2 to pi over 2, now this is 1-to-1. You know, it's a function. It passes the vertical line test, but if you didn't have the domain restriction, you did the horizontal line test, well, yeah, it's crossing over here and it's crossing over here too. But now with the domain restriction, it passes both the vertical and the horizontal line test. It passed the vertical test because it's the tangent function without the domain restriction, right? You can draw a vertical line anywhere, up and down, all the way to infinity, the tangent function, and it's never going to cross at more than one point. Horizontal line test is a different story. So, but now with the domain restriction, it's a 1-to-1 function. And so you can solve for the inverse tangent. You switch y with x like we did with sine, and then you apply the inverse, and that's how you get the inverse tangent function. Y is equal to tangent minus 1 of x, or y is equal to arctangent x. And now the graph, okay, so in blue, that's tangent x, and red is inverse tangent. And there's y is equal to x, and you can see the blue curve is just flipped about y is equal to x. Now, when it comes to inverse functions, what you can remember is that if you have a function that has asymptotes, horizontal or vertical asymptotes, the asymptotes flip. So like with e to the x, or b to the x, the exponential, it had a horizontal asymptote at y is equal to 0. Well, in log, it gets flipped, and there's a vertical asymptote with log at x is equal to 0. So that we know tangent has vertical asymptotes, and that would be at the endpoints of the domain here. So it's going to be flipped, and we're going to have horizontal asymptotes on inverse tangent. And that makes sense because it makes sense in that the domain of inverse tangent is going to be all real numbers, because if we're asking the question, what angle, or if we have a value, what angle of tangent does this, when you take the tangent of that angle, does this value correspond to? Well, the tangent of an angle can be any real number from negative infinity to infinity. So when you inputting into the inverse tangent can be any number, okay? And when it comes to the outputs we can get from inverse tangent, it's going to be any number between any angle between minus pi over 2 and pi over 2, but not including the endpoints. Not including minus pi over 2 and pi over 2, because that's the vertical asymptotes on tangent. And the idea is if you input a bigger and bigger and bigger value into inverse tangent, it's going to be getting closer and closer and closer to the angle that, if you said inverse tangent of 1 billion, then that's going to be the angle of, when you take the tangent of an angle and you get 1 billion, what comes out of it is 1 billion. That's going to be something close to pi over 2. Because when it comes to tangent, as you're getting closer and closer and closer to pi over 2, it's just getting, the tangent's getting bigger and bigger and bigger and bigger all the way to infinity. Okay? So that's inverse tangent. Y is equal to tangent minus 1 of x, or y is equal to arctangent of x, means that x is equal to tangent of y. So you take whatever the y value that comes out of the arctangent, if you took the tangent of that would give you the argument that you input into inverse tangent, where the angles that the angles that we're speaking of are only between minus pi over 2 and pi over 2. Okay. So inverse tangent, domain minus infinity to infinity, range minus pi over 2 to pi over 2. The function is continuous everywhere, and it's increasing. It's always increasing, similar to inverse sine, or just like inverse sine. It has, just like inverse sine, it has one x and one y intercept at the origin, and it has a symmetry. It's an odd function. So inverse tangent of minus x is equal to minus inverse tangent of x. And it also has two horizontal asymptotes. Okay. Now, the inverse trig functions of secant, cosecant, and cotangent, they don't go into the details here, but it's the same. You can derive those with the same process. So if we think about, let's think about secant, we know that secant is like, so it goes, it's like this. There's kind of the base sketch, the way we sketched the base period. We used this going from, it was minus pi over 4, and then this went all the way to 2 pi from minus pi over 4. So it was, oh no, minus pi over 2. This is minus pi over 2, then 0, then pi over 2, then pi, then 3 pi over 2. That was, the period is 2 pi, and this is for secant. This was the, the kind of the starting period. This is the most simple period. So this is where we're going to apply the domain restriction, somewhere in here. And so if we think about, okay, what encompasses the full range of secant? Well, okay, we could go from 0 to pi over 2, and then go from pi over 2 to pi. So the range of secant is 1 to infinity as well as minus 1 to negative infinity. So if we say, y is equal to secant x is not 1 to 1, but y is equal to secant x with going from 0 to pi over 2, not including pi over 2 because it's a vertical asymptote, that in union with pi over 2 to pi, including pi, then this secant with this domain restriction is 1 to 1. And then that encompasses the full range. You get, going with this domain restriction, you get every single value that's in the range of just secant, going from 1 to infinity and minus 1 to negative infinity, and you get all those output values just one time. And so if we take a look at the graph, okay, so the blue is secant x with the domain restriction, and the red is arc secant. And do like that. And so, yeah, you flip the blue here about y is equal to x, and you flip this about y is equal to x, and there you go. And we're going to have, so secant with the domain restriction has one vertical asymptote, and so we're going to get one horizontal asymptote in arc secant. All right, and it's a similar idea when it comes to inverse cotangent and inverse cosecant. So we can come, here's a summary of the inverse trig functions. So the domain of the inverse trig functions is the range of the regular trig function, the full range, including every possible value that you can get from that trig function, sine and cosine minus 1 to 1, tangent minus infinity to infinity, cotangent minus infinity to infinity, and then there's, these are the domains of the trig functions. These are the ranges of the regular trig functions. They become the domains of the inverses, which makes perfect sense. And then the ranges of the inverse trig functions are just based on the restriction that we made in order to make the trig function 1 to 1. And we just chose the simplest interval that would encompass the full range. And so that was every time it was either minus pi over 2 to pi over 2 or 0 to pi. And so that's what they're talking about. The quadrants here were 1 and 4 for sine, 1 and 2 for cosine. We went 0 to pi, right? So it's either going to be 1 and 2 or 1 and 4 every time. Even for like cosecant, we just did 0 to pi, and it's going to be the same idea with secant and cosecant. No, here with secant, we did 0 to pi. Cosecant's going to be minus pi over 2 to pi over 2. And you're not including they have this union here because it doesn't include the vertical asymptote. Okay. The inverse circular functions are formally defined with real number ranges. However, there are times when it may be convenient to find degree measured angles equivalent to these real number values. It is also often convenient to think in terms of the unit circle and choose the inverse function values on the basis of the quadrants given in the preceding table. So yeah, so we've been working with, in this video, in the previous video, we've been working with thinking about the inverse functions in terms of degrees. That's completely valid. You can think these inverse functions are valid for any unit of angle, because you can think about the general definition of trig functions from the perspective of any unit of angle. It doesn't matter, right? The trig function definitions have no marriage to degrees or radians. Where you're saying, you can make any measure you want, any unit you want. It's the amount of opening here. You have this common vertex here, these two straight sides, this amount of opening. You call that an angle, whatever unit you want. We know what the sine, cosine, tangent of this angle is. We use the definition of the trig function. And the inverse trig functions it's the exact same concept. If you were dealing with inverse sine or inverse, let's say inverse cosine, well, the idea is that, okay, I've got a value that I know that it was the cosine of an angle was taken. Whatever the angle, whatever unit the angle's in, the cosine of an angle was taken and I got this value. What angle is that correspond to? Well, okay, it's whatever the units are, it's going to be something between the positive horizontal and the negative horizontal. We call that 0 to pi or 0 to 180, but whatever it is, this the positive horizontal to the negative horizontal. It's going to be whatever angle that is, and then you just figure it out with what's the number you have, what's the ratio of the side lengths, and figure out what angle that corresponds to. And then when it comes to, once you have that angle, if you want to think about the general question of okay, outside of just 0 to, or the positive horizontal to the negative horizontal, what other angles would satisfy the question of if I took the trig function value of that angle, the cosine of that angle, I would get this value. It's okay. It's going to be any angle coterminal with that angle, whatever the units are, or if it has the same reference angle and the same sign. So with cosine, that would be the third quadrant. If whatever angle has the same reference angle as this in the third quadrant is also part of answering that question. I'm just trying to illustrate the units have nothing to do with everything we've talked about with inverse trig functions. The units have nothing to do with it. You can do this. Everything works for any unit of angle you want. Okay, so now here they say determine like arctangent of 1 in degrees, but we've already been doing this throughout this video and the previous video. So, but we'll work more example problems so you can get a feel for it. And I'll keep switching between the dialogue between degrees and radians, but I've already kind of been doing that. So now it talks about the idea of using your calculator to get the inverse trig functions. And so we haven't used the calculator up to this point because every example problem we've worked has been involving a special angle or an angle with a reference angle that's a special angle or a quadrantal angle. But it's the same idea. So it's the same idea as with when you use your calculator for trig functions, to evaluate trig functions. I mean, we still use the calculator for special angles, but really the calculator is the power of it is for giving you like approximations of trig function values that you can't get on your own, right? Like, well, you could, but you have to use like a numerical method. You can't get an exact value of it with a reference triangle, right? So like cosine of 12, it's not that easy to get that on your own. You can't get an exact value of it. So, but the calculator does like a numerical approximation in the background and gives you a very accurate answer. Same thing with inverse trig functions. If we were doing, if it's hard to see it clearly, but like, okay, yeah, here, inverse cosecant of minus 3. Well, just thinking about the 30, 60, 90, and 45, 45, 90 triangles, there's no, if we had minus 2, well, I can think of, you can get a ratio of 2 over 1 or minus 2 over 1 with the 30, 60, 90 triangle. I can't think of any way we could get minus 3 over 1. Now, maybe if we looked at the sum, we know with the trig, the sum and difference identities, we can get exact values for angles that are multiples of 15, but that seems kind of complicated or a little bit involved to look into all that, maybe to see if that applies here. So, if we thought about, so okay, cosecant. Let's look at this cosecant. What angle if you took the cosecant of that angle, you would get minus 3. That's what this is going to give us. And so, but that there's infinite angles that actually would give you that value, but we know with cosecant, we're restricting it to, was it minus pi over 2 to pi over 2? Yeah. So we're looking strictly from here to here. It's going to be an angle from minus pi over 2 to pi over 2. We know that there is one unique angle between minus pi over 2 and pi over 2. When you take the cosecant of it, it's going to give you minus 3. All right. So now let's continue to think about this. So cosecant, that's the reciprocal of sine. Sine is positive in quadrant 1, negative in quadrant 2. So this angle is going to be in quadrant 2 somewhere. All right. Now, well, before I draw the line, if the cosecant of this angle is going to be the minus 3 over 1. So we know that cosecant is hypotenuse over opposite. So the hypotenuse is going to have length, we can think about it as having length 3, and the opposite is going to have length 1. So in that case, we'll draw it something like this they'd be equal. The hypotenuse and opposite would be equal. So the hypotenuse is going to be longer, so it's going to be somewhere over here. Okay, so this is the angle, theta, and we can say this is going to be minus 1, right, because we're going down, x, y, and this would be 3. The cosecant of this angle theta is 3 over minus 1 minus 3. Okay, so but what is that angle, though? What is that angle? The issue is we don't have a reference triangle that we can draw that will tell us, the 30, if it was cosecant of minus 2, then we'd have 1 root 3, 2. Cosecant of minus 30 is minus 2. But it's not minus 2, it's minus 3. And so the calculator is going to use some like a numerical method to get this angle for us. It can't get there's no way to get an exact value like 1 over 2 or root 2 over 2 for this particular angle. So it uses a numerical method and gives you 0.978148. And there you go. In degrees, that's, let's see. Or wait, no, this was cosine of 12. So I need to do inverse cosecant of minus 3. And this looks like it's going to be something like minus 12 degrees, minus 15 maybe. Minus 20-ish. Okay. Now, but one thing to note, though, and we're going to look at some examples, I think in the next example, is that if we did want to know what this angle here, what's the sine of this angle or the cosine or any trig function, we could get the trig function values, any one we want of this angle. We might not be able to get an exact value for what it is without using the calculator. Well, the calculator can't give us an exact value, but I'm saying that without using the calculator gave us an approximation for what this angle is, but we could still get an exact value for any of the trig functions for this angle, because we could say, so 1 squared plus x squared is equal to 3 squared, or no, so minus 1 squared is 1, 3 squared is 9, so this would be 2 root 2, and there you go. You could get any trig function value of this angle that you want. Okay, caution, be careful when using a calculator to evaluate the inverse cotangent of a negative quantity. Enter the inverse tangent of the reciprocal. Yeah, this is, we're ignoring all this. This is talking about like when you know, if you want to take the inverse of something, you have to, if you want to find cotangent or inverse cotangent, you have to take the reciprocal, but we don't. With our calculators, the modern calculators are powerful. We've got all of the any operation we want, inverse, secant, cosecant, anything. Okay, so now, yeah, so if we wanted to get the sine of the inverse tangent of 3/2, all right, so let's think about inverse tangent of 3/2. It's what angle, when you take the tangent of that angle, do you get 3/2? However, we're restricting it to where the possible angles it's going to give us are between, with tangent minus pi over 2 and pi over 2. So, okay, there's some angle between minus pi over 2 and pi over 2 that when you take the tangent of that angle, you're going to get 3/2. There's only one angle in that region that's true. Okay, now, so tangent is, let's see, it's positive in quadrant 1, negative in quadrant 2. So we'll draw, it's going to be some angle in some acute angle in quadrant 1. Now let's see, tangent is opposite over adjacent. So the 3, it's going to be something above 45. Okay. So there's the angle, opposite over adjacent. Okay, so this inverse tangent of 3/2 is this angle here. Now, we could try and figure out what that angle is. Maybe we can get an exact value using a reference triangle. I don't think we can. Or we could use our calculator to get an approximate value, but the question is just asking what is the sine of that angle. So we don't need that angle itself. We just need the sine of that angle. So we just need opposite over hypotenuse. Well, we can get the hypotenuse here. So 2 squared is 4, 3 squared is 9. You take the square root of that, you get, so this is root 13. Okay, opposite over hypotenuse, 3 over root 13. And they rationalize that, 3 root 13 over 13. There you go. And they do another problem similar to that, and we're going to work more example problems like that. Okay, finding function values using identities. So here we've got cosine of arctangent root 3 plus arcsine of 1/3. The key to looking at what they're trying to illustrate here is kind of similar to what they were trying to illustrate in the previous example, is that like the arctangent, the inverse trig function of anything, any inverse trig function, it's an angle, right? You've got the cosine of this angle plus this angle, okay? Like arctangent, arcsine, whatever, of something, that's an angle. So we have cosine of one angle plus another angle. We can use the sum identity for cosine, okay? And that's what they do. And we'll work examples like this. Here, tangent of 2 times arcsine of 2/5. This is an angle. You have tangent of 2 times an angle. You can use the double angle identity for tangent to simplify this. Okay. Writing function values in terms of u. So we have inverse tangent of u, the sine of inverse tangent of u. Can we simplify this? Is there a way we can simplify this? Well, okay. The inverse tangent of u, it's so what value what angle when you take the tangent of that angle do you get u? So that means that this angle is going to be something between minus pi over 2 and pi over 2. But u is a variable. U can be positive or negative. So what they do is the idea is, so here they put like a theta and minus theta. And u you can write as u over 1. So the horizontal angle is going to have magnitude 1. the opposite of the angle. So opposite, we have opposite over adjacent. The opposite is going to be u. Here it's going to be u, here it's going to be u, but u is positive up here and negative down here, right? Because u is a variable. It can be positive or negative. So in either case, if you took the tangent of this angle, you get u. If you took the tangent of this angle, you get u. Where these are the same angle, just the same magnitude angle, just one is positive, one is negative. Okay, then they can use the Pythagorean theorem to get the hypotenuse. And the idea here is that for if theta is in the first or second quadrant, this is the exact same value as this, and the 1 is the exact same no matter what. The only difference is that in the first quadrant case, u is positive. In the second quadrant case, u is negative, but that's just the variable u, right? The variable u as it is can be positive or negative, like x can be positive or negative. So if you want to think about the sine of this angle, inverse tangent of u, which could be either theta can be positive or negative. So theta is like a variable as well. Theta can be positive or negative in the same way u can be positive or negative. Then the sine of theta is just u over square root of u squared plus 1. You don't need a plus or minus because it's whatever, like, so the reason why you don't need a plus or minus, so here's u over square root of u squared plus 1, they rationalize and get this. So sine of theta is, it depends, once you pick the u value, the u could be positive or negative, then that's going to make sine theta positive or negative. That's going to dictate what the theta is, because the theta is a variable. It depends on the u that you pick. Okay, finding the optimal angle of elevation of a shot put. The optimal angle of elevation theta for a shot putter to achieve the greatest distance depends on the velocity v of the throw and the initial height h of the shot. One model for theta that attains the greatest distance is, so this is the optimum angle. If you know your shot put velocity that you're going to throw it at, you've done enough throwing, you know your velocity, and you know like the height that you release it, because you have your own height and you know kind of like right below your head, then there's an optimal angle that you can try and throw at to maximize the distance, and you calculate that with the velocity you throw it at and that height of the shot of where you release the shot put. They could probably get velocities with tracking, like radar systems that, not radar, but laser systems that they can calculate their exit velocity of the shot put. And so then you can try and optimize that angle that you throw. And so they say that if they have an athlete with the height of the shot put is 6.6 feet and the velocity of release of the shot put is 42 feet per second, what's the angle? And so you just plug all that in and take the inverse sine and get the angle. And and the way you think about this though is that you would use you use like physics, engineering, Newton's laws to model this motion here, this path of the shot put based on the mass of the shot put, the force, and different things, and you could get a model for this path, and within that model would be theta. Like one of the inputs would be theta. Like you get the position as the x position and the y position as a function of time, and that would include theta. But then if you want to solve for theta, then you do algebra and trigonometry. We're going to learn how to solve trigonometric equations in the next section. You're going to need to use an inverse trig function to get the theta out of the trig function and solve for theta. So like they used Newton's laws to get a model for this path. So the x position, the y position, and that was a function of theta, but then they solved for theta. And they had to use the inverse trig function, inverse sine here to isolate the theta, to get it out of the trig function. And again, that has to do with solving trigonometric equations, which we're going to look at in the upcoming sections.